Hello. Let me quickly recall what we have proved in the previous lecture. In the previous lecture, we defined what a vector space is over an arbitrary field F. Among other things, we proved that if I give you a spanning set, meaning a subset of a vector space that spans the entire vector space. Again, that means every vector inside this set, every element of this set can be written as an F-linear combination of these elements. So whenever I give you such a set, we can find a subset of this set, make it ordered, and get a basis for this set. We also showed that if I give you two different bases, then they are going to have the same size. So if B and B prime are two bases of this vector space, then they have the same size. We call this size, this number, the dimension of this vector space over the field F, and we denoted this by dim of V sub F to emphasize that the field that we are taking is F. Among other things, we also defined the quotient space. So if I give you a space V and a subspace W, we define the quotient space of V by W. We proved that dimension of W adds up to the dimension of V over W, and then we get dimension of V. So we have this nice equation. We also proved the first isomorphism theorem in the context of vector spaces. So assuming that F from V to V prime is an F-linear map, we showed that F bar that sends a coset representative given by the vector V to the value of F at the vector V is going to define an isomorphism from the quotient vector space V modeled by the kernel of F to the image of F. In particular, they have the same dimension, and that gives us essentially the kernel image theorem, or sometimes we call it the nullity rank theorem if we interpret this equality in terms of a matrix. Okay, so we get the dimension of kernel plus the dimension of image is the same as dimension of the domain. So we can think about it as a kind of conservation law that some vectors might be killed by F, some vectors will survive, but the total dimension will remain the same. We also observed that any vector space at the end of the day is isomorphic. So any vector space with finite dimension is isomorphic to F to the n, where n is precisely the dimension of the vector space. And the isomorphism can be described by fixing a basis for the vector space V. So suppose the ordered set V1 da Vn is an F basis of this vector space. In that case, for any given vector V, we can write down this V as an F-linear combination of VI's in a unique way. And that means I get an n-tuple of elements inside F, and this vector is uniquely determined, after fixing the basis B, is uniquely determined by V. Therefore, we are getting a function from capital V, from the vector space V, to F to the n, and we discussed that this function is indeed an F-linear map, which is a bijection, and therefore it's an isomorphism of F vector spaces. Now, what we want to do today is to use this concept of dimension and basis and so on, and get more information about fields and field extensions. So let's see what I mean by that. For instance, we have already started with this discussion that if I give you a field F and a polynomial, a non-constant polynomial, let's say a polynomial of degree n with coefficients inside this field F, and then if I look at the quotient ring of the ring of polynomials modeled by the ideal generated by f, then every element inside this is uniquely determined by, can be uniquely written of this form. That every element here can be uniquely written as c sub 0 plus c sub 1x plus c sub n minus 1 x to power n minus 1. So every element here can be written as a coset represented by a polynomial of degree at most n minus 1, and this coset representative is unique. This is what we proved using long division, and based on that, we can get that, in fact, if I look at the cosets that are represented by 1, x squared, x to power n minus 1, and I put a bar on top of 1, x, and so on in order to make my notation a bit more compact, then this ordered set of n elements form an F basis for this quotient ring. So this quotient ring has dimension n, and these elements, this ordered set, forms an F basis. In particular, whenever I give you this quotient ring of f bracket x modeled by an ideal generated by f, the dimension of this vector space over f is precisely the degree of this polynomial f. And I've already pointed out how the proof goes. Essentially, we use the long division. We get that every element inside this quotient ring can be uniquely represented by a polynomial of degree strictly less than n. Then I can use the definition of a scalar multiplication and notice that this element is precisely the linear combination of x bar to power i's with coefficients c sub I. And because we have this equality, that means every element is in this f span of the vector of the elements 1 bar, x bar, and x dot x to power x bar to power n minus 1. And because of the uniqueness, we deduce that they are indeed f linearly independent. So this implication that if I have this equality because of the uniqueness, 0 is also summation of these things by coefficient 0. Because of the uniqueness, we can deduce that all the coefficients are 0, and that means that these elements are linearly independent. So we have linear independence and we have the spanning property. All together we get the claim that these guys form a basis. Now, by a similar argument, we can deduce the next example, that if E is a field extension of F, and I give you an algebraic element of inside this field E, then the ordered set 1 alpha, alpha squared, alpha to power n minus 1 is an F basis of the field f bracket alpha. Remember, we have showed that if alpha is an algebraic element, by adding alpha to the base field f and considering all the polynomials evaluated at alpha, so that forms a field. And we showed that every element of this field can be uniquely written as an F linear combination of 1 alpha dot alpha to power n minus 1. And that means the dimension of this, this field over F as a vector space over F is precisely the degree of the minimal polynomial of alpha. So here you see in this notation, it is kind of crucial to emphasize what field is going to be my base field. So over what field I'm considering this vector space. For instance, f bracket alpha itself is a field, so I can think about it as a field over itself, in which case the dimension would have been only 1, because then everything can be generated by a single element that is 1. But here I'm thinking about it as a vector space over the field f. And then I do need to point out that again, every element inside this field can be uniquely written of the form c sub 0 plus c sub 1 alpha plus the dot c sub n minus 1 alpha to power n minus 1. And that means, first of all, 1 alpha dot alpha to power n minus 1 is a spanning set. The span of this set is the entire field f bracket alpha. And second, because of the uniqueness, we deduce that they are f linearly independent. Okay, so far we have some basic properties, basic connections between what we have already discussed on fields and algebraic elements and linear algebra over an arbitrary field. But let's do it further. Let's go further. And another example is the following, that if I give you a finite field, so suppose f is a finite field, so, and I tell you V is a vector space over this finite field, and the dimension of V over F is n. In that case, we can understand what is the cardinality of this vector space. Then the cardinality of the vector space V is the same as cardinality of F raised to power n. So why is that the case? We have already proved that whenever I give you a vector space of dimension n, then as a vector space, it is isomorphic to f to the n. Because by assumption, dimension of V over F is n, as a vector space, it is isomorphic to f to the n. In particular, they have the same cardinality. Therefore, cardinality of V is equal to the cardinality of f to the n, which is cardinality of f raised to power n. As we have pointed out, when I defined a vector space, we pointed out that whenever I give you a ring A and a subfield F, then we can view A as an F vector space. So here we are mostly interested about fields and field extensions. So in this case, when I give you a field extension, E is a field extension of F, then I can view E as a vector space over the field F. And instead of writing dimension of E over F, we often write that square bracket E dots F, and we call this the degree of this field extension E over F. So again, the point is that in our study, we are going to fix F, and then we are going to add algebraic elements one after another to F. So essentially, again, if you remember, our goal was to understand the zeros of binomials. I give you a binomial, and then you find its zeros, add it to the base field F, you get a larger field. So this is a kind of a mechanism that we have done so far. So that means that we start with this base field F and then build upon that. So these field extensions are the objects that are going to be important for us. And so that's why we are introducing this concept. We are viewing this dimension of E over F as some property of this field extension. Because again, the field extension itself is going to be an object of importance for us. So the dimension of E over F we denote it by square bracket E dots F. And we call this the degree of this field extension. Okay. Now, an immediate corollary of the previous lemma and this notation, so actually I do not use this notation in the next corollary, but nevertheless, it is in the same framework that I have a field extension, is the following, that if fp to the n is a field extension of fp to the n, or alternatively, if fp to the m can be embedded into fp to the n, then m divides n. So we've seen this as part of questions in the discussion and problem session. So there I suggested another route on how to show this statement using cardinality of the group of units of these fields. And so if I look at the group of units of fp to the n, it has p to power m minus 1 elements. and the group of units of fp to the n has p to the n minus 1 elements. If I can embed fp to the m into fp to the n, then the group of units of the first field is a subgroup of the group of units of the second one. From there, we deduce that p to the n minus 1 divides p to the n minus 1, and this was the route we took in order to show m divides n. But here we see that immediately out of the fact that fp to the n is a vector space over fp to the m, we get that m divides n. So let's see why this is the case. So assuming that fp to the m can be embedded into fp to the n, I can view fp to the n as a vector space over this smaller field. That means by this result that we have over here, the cardinality of this field, which is p to the n, is indeed a power of the cardinality of fp to the n. So that means fp to the n cardinality is the cardinality of fp to the m raised to power d, and that's equivalent to saying that p to power n is equal to the p to power m raised to power d. Again, that is automatic that we get n is a multiple of m. So we see that here we do not need to know much about structure of these fields and their units and so on. What was crucial is that fp, the smaller one, is a field, and then I can view the larger one as a vector space over the smaller one. So this is what was crucial. Okay, so now what we are going to prove, and it's going to play an important role in a study of field extensions, is the so-called Tower rule. So we are given a tower of field extensions. So E is a field extension over F, is a field extension of F, and L is a field extension of E. So I am getting the tower of these field extensions. In that case, if I ask myself, what is the degree of the field extension L over F? The answer is that it is the product of the degree of the extension L over E times the degree of the extension E over F. Okay, so that means the following. So again, the degree of the field extension L over F is equal to the degree of the field extension L over E times the degree of the field extension E over F. Okay, so let's see how we go about this. So what we will do, here I'm assuming that the degree of the field extension L over E is finite and the degree of field extension E over F is also finite. Let me also point out that it is if and only if, meaning that if I tell you the degree of the field extension L over F is finite, still we get that both the other ones are finite. That's rather easy to see. But let's see how the proof goes. Because we are assuming that the degree of E over L is finite, the degree of E over F is finite and the degree of L over E is finite. That means that I can find a finite basis of L as a vector space over E. So suppose that the spaces is L sub 1, L sub 2, L sub m. So this ordered set of elements inside L form an E basis. Similarly, suppose that this ordered set of elements inside E form an F basis. Then, when I multiply an element in the first basis by an element in the second basis, but remember the base of the field, I mean the field of vector space differs in these bases. The first one is an E basis, the second one is an F basis. When I look at this product, what we want to show is that these L sub I, E sub j's form an F basis for the field L. So if we show this, then there are m times n of these elements. From there, we can deduce the dimension of L over F as an F vector space is precisely m times n, and the claim follows. In order to show that this set can be, after we order them, we get a basis of L over F, we need to show that they form a spanning set, meaning the span of this set is the entire L, F span of this set is the entire L, and second, they are F linearly independent. Here, let me emphasize that I mean the F span of this set is the entire set L. Okay, let's start with step 1, where we want to show that the F span of this set is the entire set L. That means what? I give you an arbitrary element, small l, of this field, capital L, and I want to show that this element L can be written as an F linear combination of the elements L sub I times E sub j's. We start with the fact that L sub i's form an E basis for the set capital L. Therefore, every element small l can be written as an E linear combination of these elements. Therefore, I can find some coefficients inside the field capital E and write down L as this E linear combination of L sub i's. Now next, I ask myself, okay, where are these X sub i's? These X sub i's are inside E. Every element of E can be written as an F linear combination of E sub 1 dot E sub m. Therefore, X sub i's can be written as an F linear combination of E sub 1, E sub 2, and E sub n. So I can find these coefficients Y sub I sub 1, I1, Y sub I2, dot Y sub IN. So I'm using double digits for the indices. So the first I indicates which one of these X sub i's I'm picking. I'm taking X sub I. That's why I'm choosing this I over here. And the second index tells me that I'm dealing with a coefficient of E sub j. So I can find these coefficients inside the field F and write down X sub I as this F linear combination of E1, E2, dot E sub n. Now, if I plug in these X sub i's into this first equality that we had, well, we end up getting that L is, okay, so we knew that L was summation of X sub I times L sub i's. Then we plug in, instead of X sub I, we plug in this F linear combination of E sub j's. So I can find this Y sub ij times E sub j, and the summation of those form give us X sub I. Now I use the distribution law and reorder the parentheses, and I get that the whole thing is a linear combination of E sub j's, L sub I, or L sub I, E sub j's with coefficients inside F. So we end up writing L as an F linear combination of the vectors that we were considering. Okay, so the second step is to show that these elements are actually F linearly independent. So we take a linear combination of these elements, assume that this linear combination, this F linear combination, is actually 0, and we are going to show that all the coefficients are 0. So suppose we call the coefficients Y sub ij's. That's the coefficient of E sub j times L sub I, and I assume that this coefficient is inside F. What I do is kind of undoing what we have done up here, and I'm going to reorder the parentheses, isolate L sub I for a fixed I, and put together all the terms that have L sub I in common, which means I end up getting this summation, this F linear combination of E sub i's. But remember, F is a subfield of E. E sub i's belong to the field E. This means that this coefficient, this summation, this F linear combination of E sub i's is indeed an element of the field E. What do we know about L sub i's? L sub i's form an E basis of L. In particular, they are E linearly independent. Here, we are getting an E linear combination of L sub i's that's 0. But because L sub i's are E linearly independent, we deduce that all the coefficients should be 0. So we get that these linear combinations are actually 0. Now, we turn our attention to E sub i's, E sub j's. We know E sub j's are F linearly independent, and the coefficients that we are getting up here, they are inside the field F. From here, I can deduce that these coefficients are 0. That means Y sub ij's are actually 0 no matter what I and j we pick. So these two together imply that this set that consists of elements of the form L sub I, E sub j, and this form an F basis for the field L, and therefore the degree of the field extension L over F is the number of elements of this set. There, for the index I have m choice, for the index j I have n choices, and therefore the whole thing has m times n choices. But the cardinality of L sub i's give me the field extension, the degree of the field extension of L over E, and n is the degree of the field extension of E over F. All together, we get the Tower rule. But let's see how we can use this Tower rule. So here is one example on how we can use the Tower rule. Suppose I give you a field extension of Q. I don't know what it is. The only thing that I know about this field extension is the degree of the field extension. We are told that the degree of the field extension is a power of 2. Now from here, I want to show that x to the power 3 minus 2 is irreducible in the ring of polynomials with coefficients inside E. So E is quite larger than Q, but nevertheless, I want to say that x to the power 3 minus 2 remains irreducible. Okay, let's see how the proof goes. Suppose to the contrary that this is not the case. Suppose x to the power 3 minus 2 is not irreducible in E bracket x. What does that mean? Notice that this is of degree 3. And for degree 3, we have irreducibility criterion. We know that a polynomial is irreducible, polynomial of degree 3 is irreducible precisely when it has no 0 inside the field. So now, assuming that it is not irreducible, we can deduce that there is a 0 of this polynomial inside the field E. But notice that by the Eisenstein's criterion, we do have that x to the power 3 minus 2 is irreducible in Q bracket x. In particular, that means, because alpha is a 0 of this polynomial, it means that the minimal polynomial of alpha over Q is precisely x to the power 3 minus 2. And so the degree of the field extension of Q bracket alpha over Q is precisely 3. Now I can use the Tower rule. So notice again, now I have this picture. I have E, alpha is an element here, so that means E is a field extension of Q bracket alpha, and Q bracket alpha is of course an extension of Q. Now here we show that the degree of this field extension is 3, and the degree of this field extension is a power of 2. Now we are getting a contradiction, because this guy is 2 to the n, but this guy is 3. We show the Tower theorem, which means that the product of these this smaller steps should be the larger step, but 3 doesn't divide 2 to power n, and we get a contradiction. So again, this implies that 3 should divide 2 to the n, and that's a contradiction. Okay, so now next what we want to do is to define the algebraic closure of a field inside a given field extension. So what does algebraic closure mean? Suppose I give you a field extension E over F, and so E is a field extension of F. I want to show that if I put all the algebraic elements of E together in a set, that I'm going to get a field extension of F. But I'm going to start with a lemma saying that if E is a field extension of F of finite degree, then every element is algebraic. Okay, so let's start with this lemma. So again, E is a field extension of F that has finite degree. So that means as a vector space over F, it has finite dimension. Then every element is algebraic over F. Such a field extension is called an algebraic field extension. So here I'm just saying that E is an algebraic field extension. Okay, so let's see how the proof goes. Suppose that the dimension of E as an F vector space is n, or the degree of this field extension is n. And I give you an element, alpha, of this field extension. Then by the Tower rule, we have that the dimension of F bracket alpha over F is a divisor of n. So again, in the way that we proved it, we showed, we worked under the assumption that the intermediate fields have finite dimension, and then we showed this. But if you go through the proof, we see that it is in fact if and only if, meaning, so if I tell you that E over F has finite dimension, then I cannot give you infinitely many F linearly independent elements inside this vector space. Remember, we showed that the cardinality of F linearly independent sets cannot be more than cardinality of a spanning set. So when I tell you that E over F has degree n, automatically I can deduce that whenever I give you n plus 1 vectors inside E, they cannot be F linearly independent. So what I'm saying is that either I can use the Tower theorem, or I can simply say the result that we proved in linear algebra and say that so maybe it's better to include it here, that every n plus 1 linear n plus 1 vectors are F linearly dependent. Linearly dependent. Okay, so because of this, when I look at the n plus 1 vectors, 1, alpha, alpha squared, alpha to power n, they are F linearly dependent. That means I can find some coefficients C sub i's where not all of them are 0, in a way that this particular F linear combination of 1 alpha alpha to power n is 0. But that means that I'm giving you a polynomial, a non-zero polynomial that has alpha as a 0, which means alpha is an algebraic element, is algebraic over the field F. And this is arbitrary so this is true for every alpha inside this field extension. So altogether we get that this is an algebraic extension, field extension. Okay, now we are ready to show and define algebraic closure in a field extension. So suppose E is a field extension of the field F, and I consider all the elements inside this field extension that are algebraic over the field F. Now the claim is, in that case, K itself is a field extension of F. So first of all, it is field, and second, it contains F. The second part is not that hard, but what is crucial is why it is a field. If you think about it, it's not trivial at all, that if I tell you alpha and beta are algebraic elements, how can I deduce that alpha plus beta or alpha times beta are algebraic elements? How can I understand? I mean, it's not clear that if alpha satisfies some polynomial, beta satisfies some polynomial, what is the candidate polynomial that alpha plus beta satisfies? Okay, so this result guarantees that there is such a polynomial with coefficients inside F. The proof, however, is not direct. So I'm not going to give you a polynomial or an algorithm to how to find a polynomial with coefficients inside F if I tell you the minimal polynomials of alpha and beta. But nevertheless, we can do that, but this proof is not going to give us such an algorithm. So suppose alpha and beta are two elements inside K, which means they are algebraic over the field F. That means I can talk about the minimal polynomial of these elements. We have already discussed that when I add only one of them to the base field F, the degree of the field extension is precisely the degree of the minimal polynomial. In particular, it is finite. I can do the same for the other one. But I want to add both of these alpha and betas to the base field F. So I add alpha and then I add beta. And I notice that beta itself is algebraic over F. In particular, it is algebraic over F bracket alpha. And therefore, this field extension is also finite field extension. Now that both of these field extensions are finite, and I have this tower of fields, F bracket alpha beta is a field extension of F bracket alpha, and this is a field extension of F. So I can put one after another and deduce that the field extension of F bracket alpha beta over F itself is also a finite field extension. But in this lemma, we show that if I give you a finite field extension, that is an algebraic field extension, which means every element of F bracket alpha beta is algebraic over F. So F bracket alpha beta itself is a subset of this set K. But this is a field. That means alpha plus minus beta is inside K. Alpha times beta is inside K. And if beta is not 0, alpha times beta inverse is inside K. And F is a subset of this, and therefore F is also a subset of K. Altogether, we deduce that K is a field, and it is a field extension of F, and that's exactly what we wanted to show. This particular field extension is called the algebraic closure of E in the field extension E. The algebraic closure of F in the field extension E. Okay, so now we define algebraic closure as well using the Tower Theorem. Now let's discuss a very cute application of Tower Theorem, which goes back to a very old problem in Euclidean geometry. So in Euclidean geometry, there is this series of questions about construction. how can we construct certain values, certain angles, certain shape. What does construction mean? So, I mean, the famous questions are like this, that can we construct the third root of 2? Can we construct pi? I mean, they don't say pi, they say, can we construct the length of arc? Can we construct a segment that has the same length as perimeter of a circle of radius 1? Questions of this type. But what does construction mean? So here is a formalism of defining construction. So the intuitively construction means that we want to sketch a shape using straight edge, ruler, and a compass. And that means that when I give you 2 points, you can actually draw the line that passes through these 2 points, or draw a circle with center centered at one of these points and passes through the other one. So these are the tools that we have in hand. And I start with giving you a unit segment. So I give you 2 points, and then you start doing this kind of construction. So either you connect to the 2 points and create a line, or you take one of these points and consider it as a center, and then you can construct or sketch a circle that passes through the other one. So these things we consider as some things that we can construct. And then we get intersection points of these things that we have already constructed. And we repeat this process. Whatever we end up getting, we say that we can construct that point, we can construct that circle, we can construct that line, and so on. So these are considered constructed points. Now, we want to see if we can use this mechanism and end up getting a segment that has length third root of 2, or a segment that has length pi, or an angle that is angle 20 degrees. So these type of questions was around for a long time. But let's see how field theory can help us to address this question in a negative way. So suppose that I start with initial points that have coordinates 0, 0 and 1, 0. And I start doing constructions. I end up getting, at some point, a point that has coordinates alpha and beta. In that case, the field, first of all, alpha is algebraic element, is an algebraic element. It's algebraic over Q. And second, when I look at the degree of the field extension, Q bracket alpha over Q, similarly, beta is algebraic over Q. And when I look at the degree of the field extension, Q bracket beta over Q, both of them are powers of 2. So this is a very interesting result, and we will see how this can help us to answer these famous questions from old times. Okay, so let's start with this theorem. I'm not going to give you all the details. I'm going to just convey the main ideas on how the proof can go. Okay, so again, let's see what it means for a point to be a constructed point. It means that I have a series of steps starting from my unit 0, 0, 1, 0. We can construct a line, a circle, another line, and each time that in the steps that I go, I have 2 circles or 2 lines or 1 line and a circle with the points that we have already constructed, and then we consider the intersection points of those. Now think about it. Intersection points means what? I have to write down equations of these 2 circles, or this circle and this line, or these 2 lines. And then when I want to find the intersection points, I have to solve certain equations. But these equations will be equations of degree 1 or degree 2 equations. And these degree 1, degree 2 equations have coefficients that come from the coordinates of points that we have already constructed. So this means what? This means that each time I'm adding zeros of certain degree 2 polynomial or degree 1 polynomial to a base field that I've already constructed, and go to the next step and go to the next step. So all together, we get a chain of a tower of fields where each one, so we start with Q and then we add another element to Q that's a zero of a quadratic equation. Then I add another element to F1 that's a zero of a quadratic equation with coefficients inside F1, and so on. So this means this tower of the fields that I have, each time I'm adding a zero of a polynomial of degree 1 or 2, which means the degree of these field extensions is either 1 or 2. So either I'm not changing the field, or I'm adding only a zero of a degree 2 polynomial. Therefore, I'm getting a degree extension. The degree of this field extension would be 2. Now, if I use the Tower rule, I deduce that the degree of Fn over Q is in fact a power of 2. And alpha belongs to this final field extension that we are getting. Now, again, if I use the Tower theorem, but this time the Tower rule, but this time for this tower, considering that this field extension is a power of 2, we get that all the intermediate ones should be powers of 2, and that implies that the degree of this field extension Q bracket alpha over Q is a divisor of this power of 2, and therefore that by itself is a power of 2. And that's exactly what we wanted to show. For beta is similar. Now immediately we get that the third root of 2 cannot be constructed, and we cannot find you cannot construct a segment whose length is the third root of 2, because if the endpoints are supposed to be constructed points, and then the length would be also a quadratic equation in terms of guys that are inside some field extension that have a degree extension, a power of 2. This means that all the lengths that we can construct, if we add them to Q, we get a field extension of degree a power of 2. But the minimal polynomial of the third root of 2 is 3, which is not a power of 2. And from there we get a contradiction. So here I circled that as 3, but so here again what I meant was to say that the degree of this field extension is not a power of 2. So it cannot be constructed. Pi is even worse because this is not even algebraic, but all the things that we can construct are algebraic elements. So altogether, we get that pi cannot be constructed, the third root of 2 cannot be constructed. By similar argument, we can say that, so if I look at cosine of 20, so if I can construct an angle, then I can project it, I can separate a unit on one of the legs of this angle and then project it to the other leg, and we get cosine of that angle. So this means if I can construct an angle, we can construct cosine of that angle. But cosine of 20, one can show that it satisfies a polynomial of degree 3. In fact, using this equality and the fact that cosine of 60 is the third root of square root 3 divided by 2. Cosine of 60 is actually half. So from there we can deduce that cosine of 20 satisfies a polynomial of degree 3, and we can check that it is indeed irreducible. I leave this to you as an exercise. So in particular, Again, when I add cosine of 2 to q, the degree of this field extension is not power of 2. Therefore, this number cannot be constructed. So there was this old question whether or not we can find a general method of dividing a given angle into 3 equal parts using ruler and compass. In fact, many people claim that they can do this. But now you can see that degree 60 we can construct, but degree 20 we cannot construct. So there should not exist such a general rule, such a general method of dividing a given angle into 3 equal pieces. Okay, so now we saw a very cool application of this Tower rule. Let's see more abstract applications. Suppose E is a field extension of the field F, and I give you an element alpha inside this field extension. I tell you it is algebraic over F. Moreover, I tell you that the degree of this field extension is odd. In that case, if I add alpha squared to the same base field F, here I forgot to write down F, I'm going to get the same field extension. So that's the claim. So then we want to show that F bracket alpha squared is equal to F bracket alpha. Okay, let's see how the proof goes. The first thing that we notice is that alpha squared is already here, and therefore F bracket alpha squared is a subfield of F bracket alpha. Now that it's a subfield, I want to use the Tower Theorem for this tower of fields. So I have F bracket alpha and then F bracket alpha squared. Notice that because alpha is algebraic, alpha squared is also, so here I meant to say the other way around. So here is, because alpha is algebraic, alpha squared is also algebraic, and I have this tower of fields. Now I want to use the Tower Theorem here. What we know is that the degree of this field extension is odd. Therefore, by the Tower rule, the degree of these intermediate field extensions should be also odd. Now, let's see what we can say about the degree of the field extension at top. So F bracket alpha over F bracket alpha squared. We want to show that this is degree 1 field extension, which means they are the same fields. So that's why I'm focusing on that. But we know that, okay, so if I want to understand the degree of this field extension, I need to understand what is the minimal polynomial. So again, here is the field extension that I'm interested in, F bracket alpha over on as a field extension over F bracket alpha squared. But I'm adding a single element alpha to the base field in order to get this. So to understand this degree of this field extension, I have to understand what is the minimal polynomial of alpha over this field. We do have a very nice candidate as a polynomial that has alpha as a 0. That's x squared minus alpha squared. This is a polynomial that has coefficients inside this smaller field. And alpha is clearly a 0 of this polynomial. That means the minimal polynomial, whatever it is, should divide this polynomial. So the degree of the minimal polynomial is either 1 or 0 or 2. So it's either x squared minus alpha squared, or it has a 0, and then the degree of the minimal polynomial is 1. So in either case, the degree of this field extension cannot be more than 2. So it's either 1 or 2. But as we have pointed out, by the Tower rule, as we discussed over here, by the Tower rule, the degree of this field extension is supposed to be a divisor of this odd number. Therefore, it cannot be 2. So again, this degree of this field extension is supposed to divide the degree of F bracket alpha over F. But the degree of F bracket alpha over F is an odd number. So the degree of f bracket alpha over f bracket alpha squared cannot be 2. And we had only 2 possibilities for this degree extension. It was either 2 or 1. It cannot be 2, so it is 1. And that means that f bracket alpha can be generated by a single element as a vector space over f bracket alpha squared. So if I put 1 over there, everything is a multiple of 1. And that means that f bracket alpha is equal to f bracket alpha squared. So we get this interesting example, again, another application of the Tower rule. So let's see another example of the Tower rule. So what is it? I give you 2 algebraic elements, complex numbers that are algebraic over Q. Let's denote the minimal polynomial of alpha over Q by F, and the minimal polynomial of beta over Q by G. So they are irreducible polynomials over Q. That we know for sure. But now the question is, are they irreducible? Do they remain irreducible after I enlarge Q? So first by beta and then by alpha. And the result is that the minimal polynomial of alpha remains irreducible over Q bracket beta precisely when G remains irreducible in Q bracket alpha bracket X. So if F remains irreducible after adding beta, this happens precisely when G remains irreducible after adding alpha. So this is a result that we want to show. Let's go through the argument. First thing that we notice is that alpha, so I'm going from left to right. I'm assuming that F is irreducible in Q bracket beta. From here, I want to understand what is the minimal polynomial of alpha over this larger field, Q bracket beta. So alpha is a 0 of F. F is monic because it's the minimal polynomial of alpha over Q. F is irreducible, irreducible over this larger field. That's our assumption by characterization of minimal polynomials. That means that the minimal polynomial of alpha over this larger field is still F. That means when I add alpha to this larger field, the degree of the field extension that we get is always the degree of the minimal polynomial over this larger field. But now that we understood what this guy is, we can deduce that it is precisely degree of F, which means it's the degree of the minimal polynomial of alpha over Q. Now I can use the Tower rule. So here is the Tower rule. And then deduce that the degree of, when I add alpha and beta together, I get this. So now the degree of this field extension over Q is the product of the degree of the field extension of Q bracket alpha beta over Q beta times Q beta, the degree of the field extension of Q beta over Q. So this, by the first term, we have already said that it's degree of the minimal polynomial of alpha over Q. That second term is also the degree of the minimal polynomial of beta over Q. So altogether, we get that this field extension, the degree of this field extension is product of these degrees of these minimal polynomials. So essentially what we are doing, the game is like this, that I have this field extension Q bracket alpha bracket beta, and I have Q in the middle at the bottom. And then I'm reaching to this in 2 different routes. So first I consider beta as the intermediate field and add it to Q. And now I want to do the same, but go through alpha. And then we said, so initially we said that, okay, so assuming that F is irreducible, we deduce that the degree of this field extension here is the same as the degree of the minimal polynomial of alpha over Q. That came from our assumption, and this one is for sure always the case. So this one is, so now I'm going to the other leg of this shape and use again Tower Theorem to write down this degree of this field extension as product of these two. So I'm using the intermediate field Q bracket alpha this time. And the second term is the same as the degree of the minimal polynomial of alpha over Q. Now these two cancel each other out. So this term and this term, they cancel each other out, and we deduce that the degree of, so you see this is precisely Q bracket alpha comma beta, but I'm thinking about it as adding beta to the base field Q bracket alpha. And the way that we have computed, we deduce that this degree is precisely equal to the degree of the minimal polynomial of beta over Q. But in general, whenever I give you a field extension and I add add an algebraic element, we know that the degree is the same as the minimal polynomial of added element over the base field. So from these two, we are getting that the minimal polynomial of beta over Q has the same degree as the minimal polynomial of beta over this larger field. You see, when I allow a larger set of coefficients, most likely the degree of the minimal polynomial can drop. But how can I make it precise? Notice that the minimal polynomial over the smaller field, the minimal polynomial of beta over Q, is a polynomial in the larger field as well, with coefficients inside the larger field as well. And it does contain beta as a zero. Therefore, the minimal polynomial in the larger field should divide this minimal polynomial of beta over Q. So this type of argument is actually very useful, not only in this example, but in general. So whenever I give you a tower of field extensions, so let's say this, I have E over F and L over this guy, I give you alpha over here, I tell you that alpha is algebraic over F, then this type of argument that we had over there implies that the minimal polynomial of alpha over E divides the minimal polynomial of alpha over F, of course, in E bracket X. So these are, we are viewing these binomials in E bracket X, and the same argument as above implies that the minimal polynomial over the intermediate field always divides the minimal polynomial over the smaller field. So it's identical argument as this. It's often useful to use this rule. But in this case, by 1, we know that these polynomials have the same degree, and by 2, we know one of them divides the other one. So they are the same polynomial. Remember, both of them are monic polynomials. So they are the same polynomials. Now that they are the same polynomials, that implies this G, which is the minimal polynomial of beta over Q, is indeed irreducible inside Q bracket alpha bracket X, because it's the same as the minimal polynomial of beta over this larger field, but over a field, minimal polynomials are always irreducible. So we get the claim. The other direction is identical. Okay, so we'll continue in the next lecture.